Okay, welcome to this review of electric field. So I will start a very quick review and then give one or two examples. So the electric field is a vector. So the electric field is created by charges. Let's say we have a positive charge Q. This positive charge will create electric field, and the direction of the electric field is outgoing. A negative charge will create an electric field that is inward. So it's going toward the charge. Let's say this is a negative charge. Okay. So the electric, if we take a charge, for example, plus Q, this charge is located somewhere here. The electric field that this charge will create at a point, let's say a point A, and this point is located at the distance R. So this electric field created by the charge at a distance R is equal in magnitude to K, the value of the charge over the distance R squared. So K is this famous constant, 1/4 pi epsilon 0. Q is the charge in Coulomb, charge measured in Coulomb, and R is the distance in meters. Okay. Now, we are talking here about punctual charges. The electric field, of course, is a vector, and it has a magnitude and a direction. As I mentioned, the direction is when you have positive charge, it's an outgoing direction, and when you have a negative charge, it's an inward direction. Let's go to an example of a dipole. One examples that we usually give is an electric field created by a dipole. A dipole is a combination of two charges that are close to each other, and they have the same magnitude of charge but opposite signs. Okay, so let's consider a y-axis. This is an x-axis. So this is the y-axis, and I will take two charges. One of them is negative Q, and one of them, and the other one is positive Q. So both charges have a magnitude Q, and I would like, and then the distance here is A. So the distance from the origin to the position of the charges is A. And I am interested to look at the electric field created by those charges at a distance x along the x-axis. Okay, so I want to calculate the electric field here. We know that the electric field is a vector, and the vector follows the superposition principle, which means the electric field created at this point x will be the combination in vector of the electric field created by the positive charge plus the electric field created by the negative charge. Let's talk about the negative charge. So to do this, first I extrapolate, and the electric field created by the negative charge will be an inward. I will take it in blue. So this is the electric field created by the negative charge, and the electric field created by the positive charge, it is an outward. I will just do it as E positive. Now you can see that E minus, sorry, I can start by E plus. E plus will be equal to magnitude E plus cosine of an angle, that is this angle, I will take it as theta, and so it will be cosine theta I. I is the unit vector along I, and J the unit vector along Y, sorry, along X, along Y, plus E plus sine theta J. the same thing, we can easily see that E minus will be equal to a minus E minus cosine theta I. So it has a negative component along the x-axis. This is the negative component. And it has a positive axis, a positive component along the y-axis. Now, because both electric charge located at the same distance of the x, the point where I'm calculating the electric field, so the magnitude of E plus is equal to the magnitude of E minus at that point is equal to KQ, because both charges have the same magnitude, divided by the distance r squared. And this distance r squared is this one. This is r and this is r. And you can easily see that r is equal to a squared plus x squared. Okay, so r, this distance squared, is equal to this distance squared plus this distance. It's a rectangle triangle. Okay, now because of that, we can easily see that this component will cancel with this component. Both electric field will cancel along the x-axis because they have the same magnitude, except one of them is to the negative, is projected into the negative x-axis, and the other one is projected into the positive x-axis, which means they will cancel. So consequently, the total electric field at point x, which is the sum of the electric field created by both charges, will be 2 times E. Well, I can take E plus sine theta j. What is sine theta? Sine theta, you can see that sine theta is equal to A over R. So it's A over A squared plus x squared I. So then the total electric field will be 2 times K Q over A squared plus x squared times A over A squared plus x squared. Well, we can also do this. This is, so here it should be A squared plus x squared, just to be consistent. And this one will be, so this will give me 2KQA over times, of course, times here, A squared plus x squared to the power of 3/2. This is the, of course, along the J, along J. This is along J. So the components along J. This is the final electric field at that point X. Now, if X is equal to 0, which means I am looking at the electric field at this location here, at this location, then all what I have to do is to replace X by its value, and then the total electric field in magnitude at X equals 0 will be equal to 2K Q over, or times A over A squared, okay, to the power of 3/2, which will give me 2KQ over A squared. So this is the electric field created by a dipole at any point along the x-axis, and in particular at the center, or at in the middle of way between the positive and negative charge. So in the next video, I will talk about the electric field created by a distribution of charge, not punctual charge or point-like charges, but a distribution of charge.